Hello everyone, this is Manoj Shinde, faculty in Mechanical Engineering Department. So welcome to my YouTube channel, which is named as Thermal Engineering by Manoj Shinde. So we have started the course Turbo Machines. In that, today we are going to see the numericals on module number 3, that is steam turbines. So today we are going to start the single stage impulse turbine, the numericals on single stage impulse turbine. So today's numerical is very important from your examination point of view, that is VTU examination. Let us read the problem carefully. Steam flows through the nozzle with a velocity of 450 meter per second, which is inclined at an angle of 16 degrees to the wheel tangent. Steam comes out of moving blade with a velocity of 100 meter per second in the direction of 110 degrees with the direction of blade motion. The blades are equiangular and steam flow rate is 10 kg per second. In the first bit, we need to calculate power developed, second bit power loss due to the friction, third bit axial thrust, fourth bit blade efficiency, and fifth bit is blade coefficient. Okay, so after reading the problem carefully, let us try to write down the given data. In the first, he has given steam flows through the nozzle with a velocity of 450 meter per second. So velocity of steam at the exit of nozzle, that is V1. You can say the velocity of steam at the exit of nozzle or the velocity at which steam hits or steam jet hits the blade, that is designated by V1. Okay, steam velocity at the exit. Steam velocity at nozzle exit. Nozzle exit, that is given by V1 equals to 450 meter per seconds. 450 meter per seconds. Inclined at an angle of 16 degrees. Nozzle angle is given by alpha 1 equals to 16 degrees. So remember students, the nozzle angle is represented by alpha 1, which is of course 16 degrees. Next, steam comes out of the moving blade with a velocity of 100 meter per second. The exit velocity of steam from the blades, exit velocity of steam, exit velocity of steam, which is given by V2. As we have discussed in the previous classes also, this is a blade. The velocity at which steam hits the inlet tip of the blade is V1, and the velocity at which steam leaves the curved blade, that is V2. V2 is the exit velocity from the blade, which is given as 100 meter per seconds. 100 meter per seconds. Now the inclination of that velocity, that is exit velocity, is 110 degree. So remember guys, if the angle is given as more than 90 degrees, so we have to subtract it from 180 degrees. Okay? Okay, this is the procedure. Angle made by exit velocity, which is given by alpha 2 equals to, since the given angle is more than 90 degrees, so we are supposed to subtract it from 180 degrees. Okay, so this is 180 degree minus 110 degrees, so this is equals to 70 degrees. So we have to take alpha 2 equals to 70 degrees in the direction of blade. The blades are equiangular. The inlet tip angle of the rotating blade is equals to outlet tip of the rotating blade. Beta 1 equals to beta 2. Equiangular blades. Equiangular blades. So we have to take beta 1 equals to beta 2 since the blades are equiangular. Next, steam flow rate is m dot equals to steam flow rate is m dot equals to steam flow rate is m dot equals to 10 kg per second. 10 kg per seconds. Okay. Now here we have to calculate to find to find first bit power developed to P, second bit power loss due to friction, C bit, or third bit axial thrust Fa, fourth bit blade efficiency, fifth bit the blade coefficient, that is Cp. The blade coefficient, that is Cp. Okay. Now the next step is to draw the rough sketch of combined velocity triangle. The rough sketch of combined velocity triangle. So this is the sketch for combined velocity triangle here. So A, B, D. This is the inlet velocity triangle in which V1 is the absolute velocity of steam, which is making an angle alpha 1 with respect to horizontal. So here V1 can be resolved into three components, namely the flow velocity component Vf1, which is vertical in nature. Second one is VR1. VR1 is the relative velocity component, which makes an angle beta 1 with respect to horizontal. And third component is VU1, the tangential velocity component, okay, at the inlet of force. Right. Now here U is the tangential velocity of the blade. For an axial flow turbine, U1 equals to U2. Okay, for an axial flow turbine. Fine. This is the inlet velocity triangle. Similarly, we have to draw the outlet velocity triangle, that is FEC. FEC is the outlet velocity triangle where V2 is the exit velocity from the blade, and which V2 is also inclined in nature, which is making an angle alpha 2 with respect to horizontal. V2 also makes three velocity components, namely the flow velocity component Vf2, the relative velocity component Vr2, which is making an angle beta 2 with respect to horizontal. This is beta 2 here, and Vu2, the tangential velocity component at the outlet. So this is how we have to construct the combined velocity triangle. Since U is common, so that's why we have to combine the inlet and outlet velocity triangle. So this is not for the scale. This is just for your reference. Now the next step is, this problem we are going to solve by using the graphical method. So you should be ready with the graph paper, geometry box with calculator. Okay. Now let us start the numerical here. If this is a graph paper, here, okay. Now you have to start, you have to hold the graph like this, and you have to leave 2 centimeters from the bottom, and you have to start sketching the graph. Okay, you have to start sketching the graph. Look here carefully. Before drawing the graph, we have to select the appropriate scale. We have to select the appropriate scale. Let us take the scale as 1 centimeter equals to 40 meter per seconds. 1 centimeter equals to 40 meter per seconds. You can take 50, but don't take the larger scale. The larger, say 70, 80. In that case, we'll get the smaller graph. Uh, in that case, there are chances of getting the errors or difference in answer, much difference in answer. Okay, so try to adjust the scale such that the V1 should be more than 9 centimeter, but less than 12 centimeters, so that the graph should not cross the margin. Okay, or sometimes he will give the U value directly. So in that case, select the scale such that the U should be in between 3 to 4 centimeters. In terms of centimeter, U should range between 3 to 4 centimeters. Okay. Now, in this case, let us take the scale as 1 centimeter equals to 40 meter per seconds. Okay. But here we don't know the value of U. Let us take the horizontal line. I don't know the length of this line. And let me locate the point D here. Let me locate the point D here. I don't know the exact location of point C because U is unknown here. U is unknown. Fine. Now from point D, V1 is emerging at an angle alpha 1. So alpha 1 equals to 16 degrees and V1 is equals to 450. So while drawing the graph, we have to take all the dimensions in centimeters. Okay. Now look here carefully. So here, okay. Now here, from point D, V1 is emerging at an angle alpha. Alpha 1 is given 16 degrees and V1 equals to 450. Now here, V1 equals to 450 divided by scale is 40. Since the scale is 40, now the answer is 11.25 centimeters. 11.25 centimeters. Now keep the protractor on point D. Keep the protractor on point D and measure the angle in clockwise direction. Since the measured angle is in clockwise direction on point D here. Okay? This is the reference graph. As I said, this is a reference graph. Okay? You have to refer the graph to draw on graph paper as per the scale. Okay? Now take the length V1 here. Take the V1 length here. So V1 is equals to 11.25 centimeters and alpha 1 equals to 16 degrees. Alpha 1 equals to 16 degrees here. Okay? So we got the point A here. Now from point A, drop a vertical line up to B here. Drop a vertical line up to B and join the horizontal line. Join up to the horizontal line here. Since the point exact location of point C is unknown because U is unknown here. Okay? Should be very careful. Now similarly, from point D, B2 is emerging at an angle alpha 2. So alpha 2 is known 70 degrees and B2 value is also known. So here B2 equals to V2 is 100 meter per second. 100 meter per second. So divide by 40, you will get the value in terms of centimeters. It is 2.5 centimeters. It is 2.5 centimeters. Now keep the protractor on point D and measure the angle in counterclockwise direction. Since the V2 angle alpha is measured from counterclockwise direction, that is 70 degrees. Okay, and the length is 2.5 centimeters. This is 2.5 centimeters. The angle is 70 degrees. V2 is 2.5 centimeters. 2.5 centimeters. Okay. Hope this is clear. 2.5 centimeters. You got the point F here. You got the point F. Now from point F, drop a vertical line. Drop a vertical line up to E. Now join DE here. Join DE. Fine. So FE should be a perfectly vertical line. So this is of course VF2 here. VF2 and this is VF1. This is VF1. Now the question arises, how to get the exact location of point C? Okay, measure the value of EF, the length of EF. The length of EF or VF2 is around 2.4 centimeters. Is around 2.4 centimeters here. Is around 2.4 centimeters. Now exactly below this point, just extend this line up to 2.4 centimeters. 2.4 centimeters here. Hope this is clear. Now look here carefully. I'll repeat it once again. Just measure the length EF. I'm getting it as 2.4 centimeter. Just draw or continue this line up to the length that is equals to 2.4 centimeters. That is equals to 2.4 centimeters. Hope this is clear. Okay. Let me take this as F dash. Of course, E to F dash is again 2.4 centimeters. E to F dash is 2.4 centimeters. Now from point A, join up to F dash. Join the point A and F dash. By using the straight line, join the point A and F dash here. Okay. Now the point where this line intersects the horizontal line, that is the exact location of point C here. This is the exact location of point C, and measure the length U here. Measure the length U. Okay, in terms of course centimeters. Now its length is, its magnitude is VR1, and join F to C. Join F to C. This is VR2. This is VR2. Here you can take alpha 2, which is already given. This is beta 2, and this is beta 1 here. This is beta 1. And of course, the total length, or the total length between B to E, the total length between B to E is delta VU. Is delta VU. Now measure all the lengths here. Measure all the lengths. So you can get U equals to 4.3. You can get U equals to 4.3 here. So from graph, you can write from graph U equals to 4.3 centimeter. And if you multiply with scale factor, scale ratio 40, so you can get 172 meter per second. 172, this is in meter per second. Now the overall length from B to E is delta VU, which is equals to 11.8 centimeters. 11.8 centimeters. And if you multiply with the scale 40, 11.8 into 40 equals to 472 meter per second. 472 meter per second. I hope this is clear. Okay. Next, we have to take here VR1 and VR2 as well. This is VR1 and VR2. Let me write here. From graph, VR1 equals to, the length of VR1 equals to 7.3 centimeter. 7.3 centimeters into scale factor is 40, of course, and the product is 292 meter per second. 292 meter per second. Similarly, VR2 equals to, just measure the length of VR2 or CF. So VR2 equals to 5.7 centimeter. 5.7 centimeter. You may get some difference, the plus or minus 1 to 2 centimeters. Don't worry. Okay. 228 meter per second. 228. This is in meter per second. Similarly, try to measure the value of VF1 and VF2. This is VF1 and VF2 here. VF1 is 3.1 centimeter. 3.1 into 40. So you'll get it as 124 meter per second. Similarly, VF2 equals to 2.4 centimeter into 40. 2.4 into 40, which is equals to 96 meter per second. 96 meter per second. 96 meter per second. Okay. Hope this is clear. Fine. Now let us try to calculate all the unknowns here. Let us try to calculate all the unknowns. The first unknown is power P. So let us rub this. The first unknown is power P. Okay. Now how to get the value of power P? We know the formula for power, which is already discussed in module number 2 by using the alternate form of Euler's equation, right? We have got the equation, that is Euler's turbine equation. Okay. So power P is equals to m dot divided by Gc into U into delta VU. And if you want to get the power in terms of kilowatts, just divide by 1000 here. Just divide by 1000, you will get the power in terms of kilowatts. Now, the m dot value is 10 kg per second into U, and here mandatorily you have to substitute all the values of velocity in terms of meter per seconds only while doing the calculation. I repeat, while doing the calculation, you are supposed to substitute all the values of velocity in terms of meter per second only, not in centimeters. Okay, not in centimeters. So u is equals to 172 here. U equals to 172. Next, delta vu equals to 472. 472 meter per second divided by GC value is 1 into 100 here. The value of power is 811.84 kilowatts. 811.84. This is in kilowatts. Okay. Second bit, the power loss due to friction. Power loss due to friction. We know that the change in relative velocity component leads to loss in power, which is of course considered as power loss due to the friction. Okay. How to write the formula? We know that the formula is m dot by 2gc into the difference between relative velocity component, square of the relative velocity component. That is Vr1 square minus Vr2 square. If you want to get the power in terms of kilowatts, power lost in kilowatts, just divide by 1000 here, right? So m dot is again 10 divided by 2 into 1 here into Vr1 square. Vr1 is 292 square, 292 square minus Vr2 is 228 square. 228 square, just divide by 1000 here, you will get the value, that is power P in terms of kilowatts. That is 166.4 kilowatts. 166.4, this is in kilowatts. Okay? Now the third bit is axial thrust. The third bit is axial thrust, which is given by FA. Third bit is axial thrust FA, which is given by the formula m dot by GC into Vf1 minus Pf2. Vf1 minus Pf2. Okay, so why we have to take the negative sign in this formula? Because both Vf1 and Vf2 are in same direction. They are moving towards the same direction, that is upward direction. M dot is 10 divided by GC is 1. Vf1 is 124 minus 96, which is equals to Fa equals to 280 newtons. 280 newtons. Okay. Fourth bit is blade efficiency. We know that the blade efficiency is equals to 2u delta vu divided by v1 square into 100. So 2 into u is 172 into delta vu is 470. Okay, 472 here, 472 divided by v1 square. v1 is 450 square. And of course, you can multiply with 100 to get the efficiency in terms of percentage. Okay. So the blade efficiency is equals to so if you calculate the answer for this blade efficiency is 80.2%. 80.2%. Now the last bit is the blade coefficient, which is written as CB. CB equals to VR2 by VR1. VR2 by VR1. So you know both the values. VR2 is 228 and divided by VR1 is VR1 is 292 meter per second. 292 meter per second. So the ratio is 0.781. This is the value for CB. This is the most expected question in exams. Okay. So if you have any doubts anywhere, you can put your queries in the comment box. Okay. So don't forget to like, share, and subscribe my channel. My channel name is on YouTube. My channel name is Thermal Engineering by MODULE-3. thermal engineering by Manoj Shinde. Thermal engineering by Manoj Shinde, and my WhatsApp number is 988 653907. This is my WhatsApp number. So if you have any queries, any doubts, you can put your queries in the comments box of YouTube, or you can put your queries, you can send your queries personally to this WhatsApp number, that is 988653907. Okay, hope you all learned the concept. Thank you and have a great day.